I'm going to talk to you today about hole-driven development in Liquid Haskell, and I'm going to show you some mockups and show you some Liquid Haskell code. And my name is Patrick. I work with Gan Shen, and Lindsay Cooper, who's here, is my advisor. And we're from the University of Santa Cruz, University of California, Santa Cruz. All right, so getting right into it, this is going to talk about some things that are kind of concrete examples of what the past presenters have talked about. And so first things first, refinement types are what we're going to cover in Liquid Haskell, and then we're going to show proofs in Liquid Haskell. And then I'm going to show you some examples of typed holes in Liquid Haskell to lift that cognitive load. I'm sorry, I keep using your phrase. All right, so what are refinement types? These constrain program values using predicates. So let's look at a couple of examples. This is Liquid Haskell syntax, and the examples here are things that you might use in any practical application, such as writing proofs or in normal programs. So here we have this first example, if you can see my pointer, is an integer bound to n, and we're constraining the integer such that 0 is less than or equal to it. So that's a natural number commonly used. And the second one is a function signature with x bound to the type of a value with type A, y bound to that same value of type A, and then result z, and we're constraining the result to be the addition. And so this could be a polymorphic addition function where the specification is saying that you have to have addition here. And then this last one is integer to integer to integer, binding d to a value which is not 0. So that's your standard safe division. And you can't call this function if you don't know that d is not equal to 0. And this is all enforced by boiling these constraints down into SMD constraints on inputs and outputs. And in Liquid Haskell, you tend to write these between little comments, but in this talk, I won't do that. So a concrete example, the tail function has this partial case where if you call it with an empty list, it will crash, which as a beginner to Haskell might surprise you. And so here with Liquid Haskell, we can constrain the inputs such that the input list is not empty. And if it were empty, then you couldn't call the function. And we can also provide some useful information about the length of the output, which is a good thing to have. And once Liquid Haskell knows that the input can't be empty, you don't even need to define that case. So makes your code a little simpler, as well as preventing those bugs that would confuse beginners. And let's use a slightly more involved example. We have this association structure in Haskell, which is very commonly used. I think it's also the basis of OCaml's maps. And it's just a list of keys and values. And you could define a haskey function over those. Sorry, Discord is saying something to me. Go away, Discord. So you could define a haskey function over those, where in the non-empty case, you're simply checking if the target key is equal to the current key, and if not, you're recursing. And if you get to the end, well, then you didn't have the key. And so the key thing here with refinement types is that you could actually, with Liquid Haskell's refinement types, is that I can actually take this arbitrary Haskell code and constrain the input to the lookup function, which is a pretty great thing to be able to do, because that means I have arbitrary constraints on my inputs, and that actually can simplify the output here of the lookup function, which if you're familiar with the Haskell prelude is normally a maybe, and we don't need to do that anymore. So Liquid Haskell lets you do all these interesting things with inputs and outputs, but it has had this feature, which I highlighted a second ago, that you can take arbitrary code and put it in refinements now, and that lets you go a little bit further, a little bit beyond pre and post conditions. This refinement reflection feature has a funny name, a long confusing name, but it just means taking normal code and putting it in refinements. And so now we can ask the question, what if the post condition is a property about other functions? And that means, well, we can actually write full proofs, arbitrary properties about different pieces of our code bases. And this is really valuable, and it brings Liquid Haskell into the realm of things like perhaps Coq, which is really awesome. And so we're going to talk about proofs in Liquid Haskell quickly. They're written using equational reasoning, and the refinements make sure the reasoning is sound. That's actually a really interesting point, which I'll get to a bit later. And type checking is proof checking, which is kind of awesome, but it's also a disadvantage because it means that the feedback you're getting is pretty granular. And this is where things become really relevant to Hatra. And so with the haskey example, let's continue a little bit more. If you define an insert function, which takes a key and a value, and if the thing is empty, it puts the key value pair into the list. And if the association list is not empty, we compare for the current key. And if it is, we replace the value, and otherwise we keep the current values and recurse through. I'm getting a notification from Zoom that you can now see my screen, strangely. Hopefully you could see that the whole time. In any case, moving forward, so the property that we might want to enforce here, again, we're going to take these arbitrary pieces of Haskell code and use them in a refinement. So we're actually going to constrain and verify information about them in the refinements. And so the property here that we want to enforce, written as this type down at the bottom of the slide, takes an arbitrary key, value, and association list bound to key, val, and m, and is going to assert in the result that the result of saying insert key value on m is going to return a map where has key of that same key returns true, as in we're saying that if you inserted a key into an association, you're going to have a map where that key is present. So this is a fairly trivial property, but it's a useful thing to know. And it's a good example for what we're discussing here. And the next thing I want to point at is this is just a type proof, which isn't explained anywhere, but I'll explain it now. And so proof is simply the unit type, and we're constraining the unit type. What does that mean? It means we're adding information into the context. The post condition of this function includes this assertion, but there's no real code that's going to deal with this value. And in fact, this proof function doesn't need to be called anywhere in real code unless you necessarily wanted that fact. But so this is a way we can approach verification. So starting with that property written as a type, we could think about how we might approach it. And so again, this is the thing that we want to approach. And so we ask the question, how do we do it? We will do it by cases. And so we could talk about when the cases, when the association list is empty, we're going to do one thing. And when the association list is not empty, we're going to do another. And when the association list is not empty and the head is the thing that we want to replace, and when the head is not the thing we want to replace. So we're actually just going to follow the same cases as what we did for insert. And we have to do this manually. We have to figure these cases out manually. We have to look at the conclusion and just try to decide what those cases should be. And that's a little bit difficult. And I'm not going to go over the whole proof, it's a bit long, but here's the third case. It has an interesting thing, which is the recursion to do the inductive hypothesis. But so in this third case, you can see we know that the list is not empty, and we know that the key is not equal to k, we're in the otherwise branch. And those pieces of information are in the context. Again, this thing that you can't see, but is very important for understanding what you need to prove, because it tells you what additional information beyond the conclusion gets you there. And so that's all pretty important. And we're going to talk about that in a little bit more detail in a minute. And then there's the inductive hypothesis. So this is just what a liquid Haskell proof looks like. And it's a lot of text. And if I showed you all three branches, you would say that's a lot of text and I don't want to type all of that. And that's what we're going to talk about in this talk. Another quick aside, these bits that I've highlighted are called proof combinators. They're just normal Haskell functions with relatively simple refinement types. And those refinement types basically tie everything together here so that this does end up being a proof. And so I'm just going to very briefly tell you what's kind of happening. So this thing I've done down here is I've restated that the conclusion of the function, except I've swapped in the argument, which is this argument that the association list was not a nothing, it's a cons, and with some pattern matching. I've swapped that in. That's all I've done here. I've restated the conclusion, and then I am continuing by expanding insert, and expanding insert for the particular case of a cons, and then continuing by expanding has key. And this is all something you kind of have to think about yourself when you write these proofs. And so we want to figure out how can we get the computer to do it for us. But so liquid Haskell is interesting. It started as this thing that couldn't do these big proofs. And here we are talking about how we can write this proof that's too big to show on a slide. And in fact, there's been some past work from the LWeb team to verify a proof of 5,000 lines that took them a very long time to write, and 5 hours to check. And then there's additional past work that I was involved in, another 5,000 line proof or 5,000 line proof effort, and described as, quote, strenuous. So this is a little bit difficult, but we can do it. And so the question is, how can we make it not so difficult? And this tool has come very far from its original purpose of just doing lightweight verification, and we want to make it more easy. So how do we get more granular feedback instead of just a yes or no from the type checker? And how do we provide assistance with that? How do we build a feedback loop so that you're not just getting a yes or no answer, and there's actually the computer's going to help you to move things forward. And so let's talk about it a little bit. There are some things we could try to do, and that is actually make the context explicit and automate simplification of it. So these aren't things that you're doing in your head anymore. And especially expanding those definitions that I showed above, which is just kind of symbol swapping, and it's a little tedious and a little bit difficult to get right. Sometimes you typo it and it's very confusing, again, because of granular feedback. So moving forward, we propose to extend liquid Haskell with type tools, which is to say that have it show you something interesting when it encounters a type tool, and hopefully suggest something that it could do. And you could use this for developing functions or proofs. In our case, in this talk, I'm going to show you a proof, and it's largely mockups. And here we go. So again, that property that we talked about a minute ago, which is that when you insert into an association list, you know that the result has the key. So here's the property with a hole. We're just going to ask the compiler, what should we do next? And using that same reasoning that we just used in the previous time I showed this proof, we can just kind of say, well, we can't expand the definition of has key because we don't know what's coming out of insert. And we can't necessarily expand insert yet because we don't know what M is. And so we have to start the proof by case splitting. And this is a sort of analysis that you might program with some heuristics into liquid Haskell. And so you could imagine the computer says, I found a hole, and this is its type. And it's just going to jump straight to that suggestion that we should case split. And that's great. Control shift case split. You just got to find the key on your keyboard. That's all it takes. And so having done that, we get some new holes. And what can the computer suggest? Well, so this new hole _0 is behind the case split, and so it has information in the context, which is that that M is an empty list. So you can imagine it does some chunking, it does some computation. It figures out that if it swaps things in and expands the first definition, it can simplify this because key is equal to key. That's great because it has this additional information in the context. So, Control Shift Picard engage. We really just want to get this done, and with this level of computation, you can automate it. And automation of these branches is maybe not so interesting. And so I'm going to kind of skip through the second branch because the really interesting thing happens when the computer can't finish it for you. And so here we go. What can we do at hole number 2, which is down here in the otherwise case? So that is the case that I showed you on the proofs on the slides a little bit ago. And in that case, we know that where is it? Sorry. We know that the list is non-empty, and we also know that the first key in the list is not the target key. And so that's why we're in the otherwise case. We know these things, and the question is, how can we automate the process? And so what can the computer say? So here's the really interesting case of this proof. We know that we want the conclusion to be true, and we know these things from the case splitting and the guarding above. We know that the M is equal to this cons of some things, and we know that the K is not equal to this key. So what can the computer do? Well, it can just expand definitions, and it can expand definitions some more, and then it can arrive at this point where it can simplify a little bit. There's a K not equal to K over here, and there's a K equal to K. There's an OR here that says that either K is equal to key or this other thing is true. And so when you simplify that, well, you just get that this other thing is true. And the computer doesn't really have a suggestion. We didn't get to a conclusion here, and that's okay, because you might recognize this as the inductive hypothesis of the proof. And that's something that if you recognize, well, then you just have to hit the right key on the keyboard, because inserting it is something that you could automate. And so, find the Ouroboros key on your keyboard and do Control-Shift Ouroboros and get it done. And suddenly the proof is done. And it turns out that it's shorter than the handwritten one. I don't know if you notice. The slide I showed before was only case 3, and now we have all 3 cases on the slide. And this is because we drove it using the information in the context and not the information in our heads that made sense and made things feel comfortable. So this has been a series of mockups. It's a little bit fast, I apologize. But we're hoping to work on this in the coming quarters, and that's my 15 minutes. Thank you.